Hi, in this video we'll do just a bit of things related to parallel processing, and so this is just a bit to play and to see what different options you have in R to do parallel computing. And this appears when you consider what you can do in the R language, and even if you have a lot of packages and things that are easy to use, at some point you'll have the question of the efficiency and the speed and the memory management that you have in the program. And the thing is that the R program or the R language is not especially good with these different issues. So there are many packages that address this problem and then allow to solve questions about memory and about the performance of the computations. So for this I'm following the book by Brett Lanth, and in the last chapter, this one, it has some, say, specialized topics, and so the thing would be like what you have in the last part. It has 3 sections, and the first section is about memory improvement, like memory management improvement, how to work with really large data sets. The second part is about parallel computing, and yeah, this is the one that more or less I'm following here. And you have the script in Atenea, which is really a small script, and I've been trying a few things that you don't need really. So there are several packages for working, doing things in parallel. So I think that you know already about parallel computing, but the thing is, in computing you first do things in a sequential way, and so when a computation is very large, you end having the length of this sequence of things you are doing. And if you could break this in parts and you could run this in different machines in parallel, then of course the thing would be much more faster. So the idea is do things of this style, and the real thing would be working in a network of computers and putting things in different computers. But here we'll, of course, for simplicity, we just use one computer, and then what you can do is to use the different cores of the processor to do the parallelism. And the first package that I'm using here is called Parallel, and this one is really not for Windows, because what I'm showing now is not working on Windows, and I'm on Windows, so I can't really run this. But if you are in a Mac or on Linux, I think you could run this. So here I'm loading the library, And then I detecting how many cores are in my processor. So this is this detect cores function. So I have 8 cores. So I can do the parallel processing, selecting up to 8 different cores. And to test on those things, we have to measure the time that some computation takes, and for this we use this system time function. So this returns you the time that the operations inside take. So you have here some R commands, and system time just gives you the time that it took to process all this. So for all of this you need a large computation. This might depend on the processors, of course, because with the years the power has increased a lot. So sometimes you see things in the books, and when you try, it's like almost no time. So you need to enlarge the values you are using. So for example, here what I'm doing is generating a random normal vector using the rnorm function. So this is a vector of n values which are all normal with 0 mean and 1 deviation. And I'm just creating this vector and putting it in this variable x1. So by running this, I'm not just doing this operation, but also I'm getting the time that the operation takes. And here I have an n for the variable, so it's easy to change this and see if the number is appropriate for measuring this. So here I have 10 million values, Control R, I enter this, and now I run the normal operation, and well, you have here the time. To me it's not very clear those times that appear here. I've checked in the help for the system time, and I think that maybe this is in Windows, maybe in other systems the numbers are different. So this depends on your processor. And so for you to know, here I have an Core i7 8th generation Intel processor. And so this took like, I don't know, I think that this is milliseconds, maybe, or seconds. That maybe could be seconds, I don't know. So you have those times. User and system is like the operation, and elapsed is like the total time, I think. So maybe the number that could be useful could be maybe the last one. And I won't do this because in Windows this doesn't work, but if you are in a Mac or Linux, you could try this. This is doing the same but using the different cores. And what I do is, well, I have the system time here to measure the time, and then I'm using the operation which is this mclapply. And this is from the multicore, I think it's called package, that comes, I imagine, with a parallel package. So multicore lapply is to apply a function to different elements, and when you do this, what happens is that the function on every element run in parallel with the different cores. So here I do this mclapply, I'm putting the number of cores that I want to use, so like 2 cores here, and then I apply this function, which is the vector, but now I divide by 2 the n, and I apply this to the 1, 2 vector. So the function, in fact, doesn't depend on x, but is to run twice the function, and then the unlist is to put the things in just one vector, because this gets me a list with the 2 half, let's say, vectors. So here I'm running the n values, and here I'm running n half values, but twice in parallel. And the next line is the same with 4 cores, and so for 1, 2, 3, 4 here, and n divide 4, and the same with 8. So this is to check what happens when you use 2, 4, or 8 cores. But this is not, if I try this, Control R, you see that there is an error because this is not support on Windows. So, well, the next thing is another library which is called Snow, and this one is for working really with the W, I think is from workstations. So the goal here is to use different computers in a network, but you can also do with the cores. So I load the library. That's it. I had some problems with the versions. I'm running 4.0.0, and with some packages I had to reinstall several things. So this is a really annoying thing about this, which is that you are always with the different versions, and then having to update the packages to the versions and all of this. And okay, and first I set my, say, network for the parallel processing. So I'm doing a cluster. Here this is called a cluster with 4 processors. So this sets the 4 cores to work in parallel in that case, because you have only one processor, but the 4 cores. So this makes the cluster and gives it a name. And next you can do things with this cluster. The cluster call sets a function to the nodes. In that case, the function is just getting the name of the node. So I'm using here sysinfo. This is to get parameters about the system, and this is the name of the parameter, which is the name of the node. And by doing the cluster call, this function is applied to all the nodes. Let me put this way. Maybe I could increase this size. Yeah. And that's okay. So the cluster call does this, and so I'm getting these 4 answers with the name of the nodes. And the name of the nodes, as they come, I think, from the same processor, by default are the same. And I can use also cluster apply. What does is apply a function using arguments and then using different arguments for every node. So here I have a list with the 4 arguments. So first node gets an A, the second B, and so on. And then the function does almost nothing, just writes here the cluster, the name of the cluster, and this ready to tell that it's ready. So it's just printing something for every node. So as you see, you get this, and now there is a variation because I'm using this argument. And so now remember that we did this system time for this random generation, and I'm gonna use this cluster to do the computation. So I define n1, which is 1/4 of n, of course, because I have 4 nodes to work in parallel now. And now I'm computing the time, and the operation is a cluster apply with this cluster we have set, and the function is just the R norm, but I'm passing here the 4 arguments, so every cluster gets 1/4 of the values. So in this way I divide the generation in 4 parts. And so this is the time. And if we look at we had before, we had 0.62, and now we have 0.41. So the time is now is lower. And in general, this might be different in different machines, and sometimes it may give the impression that you don't gain too much by using the parallel computing. The general rule is that for small computations you shouldn't use parallel computing because you don't get better performance. But for very large computations, then it becomes relevant, and the parallel computing might give you a big improvement in that case. And so when you are doing neural network computations, or in general things in machine learning with very large data sets, so this might be irrelevant. The question of parallelism is not trivial, because in general one large computation maybe can be broken in parts. Sometimes the computation is really sequential, and you need the output of one part to do the next, and so on. So in that case, because this is just generating one value after the other, of course here is very easy to apply parallelism. But in more complex calculations it may be not so easy. And here, when you have your computation, you can free the resources that are being used by stopping the cluster. So that's the one example using the snow. But the snow really is oriented to something more complex, which is working with networks of workstations. So you can look at the documentation for this. Another package here is do parallel. So I load the library. I have several warnings here for the packages. I'm using 40 400, but the last version is, the current version is 404, I think, or even more than this, but well. And now what before was setting the cluster is doing this register do parallel. So here you set the number of cores that you want to use, and again I do the same than before, dividing the random generation in 4 parts that run in parallel. And here I have the system time again to measure the time, and the function that I use is this for each. For each is a loop, so it's like a for loop, but that has the parallelism. So it's a for, but instead of in sequence, the thing runs in parallel. So if I have 4 cores, here I put I1 to 4. And I also put a parameter here which is called combine, which is what to do with the 4 things that I get. And here the function that I use is the concatenation, the combining operator, because it's just putting the vectors together. So here you say what to do with the outputs that you get in the 4 cores. And here I use this do par, which is an inline operator, so it has the percent here, and here the function that I'm running. So before I defined the n1 variable, which is 1/4 of n, and so with this I'm running in parallel, but now using this other package. Control R. So I have those numbers. And here notice that this is worse, but not much worse than the snow package, but this is better, I think, than the non-parallel version. Of course, you could play with the n value to see what happens. At some point you'll have problems with memory. If you try an n which is very large, maybe you'll have memory problems, but that is another question. And so after this, what before was a stop cluster now is a stop implicit cluster. And this is it. This was just to check for the vectors, 10 million values, and the first numbers. This is a list of the variables that we have defined. And okay, so the last thing is what could be more relevant for us is if you use the library Caret, where many of the machine learning computations are built in, so using almost the same syntax you can apply different algorithms and so on. And it also works when you have this cluster for the parallel computing. So in that case you can compare times using or not the several cores. So first I load the Caret library. This is the one that gave me problems because for some reason the ggplot2 needed something that wasn't the version that I had. But now it's it's okay. And this example is the one for the credit. So the prediction of the variable that was called like default, I think, if people was paying the money back. And so this is the data we need. So I read this. No credit is a data frame with the data. And what I do is the training. This is default, which is the variable that I want to predict. Tilde, because it's from using which variables you do the prediction. Here you have this dot, that means use all the other variables to do the prediction. And then data, this is the data frame that you use. And then you put the method. And here the method is one which is called random forest. Random forest. So you are using one, well, you are building here a model using this train general function. And here in method you could do other methods. So like, I don't know, support vector machines or other kind of algorithms. So let's try first. Remember that I just stopped the cluster, so I have no parallel computing now, and I see how much time this takes. And I think that I have a problem here. Summary connection, because I don't think that I'm using any connection. I will open this again. So let's try no. As you see, it's taking time because the random forest algorithm is fairly intensive in computations. And well, now it has finished, and here we have the time. So this is, I think, the time in seconds. So it's like almost 89 seconds. And now I load the library for parallel computing. I set the cluster with 4 cores, and now I run the same. And that's the thing. So if you compare this with the previous one, the total elapsed time is now 34. So this is almost 1/3 of the previous time. And I think that the first numbers are the CPU time. So here you also see a big difference. And next I set the cluster with 8 cores. I don't know if I should stop the cluster and set again the cluster, and I run again the same thing. Of course, in general, even if you could think that the time is divided by the number of clusters, this is not the case. So it's not as faster. And now there is not much difference respect the previous case. So when you pass from 4 to 8, the difference is very small. A small improvement, but not too much. But from 1 cluster to 4 clusters, there is really a difference. So as you see, the using of the parallelism makes a difference, because if this was a computation that took like 10 hours, so the difference is important, because it could be like 3 to 4 hours. So that really is a lot of time. And well, that's essentially what we have in this script. And so just some comments. One is, okay, we have done this with the different cores in the processor, and one thing that people has used to do this is not just the processor, but the graphics processor. And this lets you, which is called GPU computations, that means graphics processing unit. That means using the graphic card to do the computations, because in the graphic cards that are the design of those cards has been driven by the video game industry. And so then you have these cards that have lots of, let's say, nodes that are like processing units, and it's like having tens or thousands or hundreds of cores. And so this is one thing that can be used to also do the computations in parallel. But this requires some special settings, and I just tried before and I couldn't really get to do computations. Maybe I will try with more time. So the basic thing is, when you have an NVIDIA graphic card, and then you can do what is called the CUDA, using the CUDA. So this is in the NVIDIA blog web, you can find those things. So if you have one of those cards, I think I have 2 cards. One, because these powerful cards take a lot of battery, and so for normal working is using a regular I don't know, maybe Intel card or something like this. But if you are doing video games or something that requires graphical power, then it uses this other. I have a GeForce GTX 1050, I think, and so I could, I think, do those things. And the first thing I was looking at some examples that to do this in R, and I found this, but there is a problem. But the first instructions is right. You have to install, which is called the CUDA toolkit. Even if you have the card, this is something that you need to install after having the card. So you go here and choose the platform, and you can install this kit. And after this, is when you can do those parallel computations. So this I did, and now I have installed. But for example, in that case, has a reference to a package that I could install, but I couldn't run because this is a bit old, and with the 4 version of R, this didn't run. And I tried this also because I have installed one 3 point something version of R, and I couldn't run this, and I think this is has something to do with Windows. So I don't know. Maybe you could end, if you are not on Windows, using something of this. But there are more packages to work with. This is the thing I was just trying. This web. This is from some book. You see, this is more for statistics, I think, but here have some computations using this. And this package is not in the CRAN repository. So I don't know, maybe it wasn't developed beyond this point. And there are other packages, but I had no time to try them. But the thing is that if once you have this toolkit installed, then you can try to use in R this processing. And for example, I found that let me see if I can. I think I have this processor, this card. And I don't know if it explains the number of okay, so I think this has well, there are several versions, but I think that mine has like 600 and something different, let's say, cores. So this is not the 8 that we had before, but much more. But if you check in Google about those things, you'll see that even with so many cores, this is only good when you have really very large computations. If not, I think that this goes worse, and much worse, I think, that the normal non-parallel computation. because I think that I imagine that doing things in parallel has this additional processing of breaking things, and so there is some balance here that only is favorable to the parallel computing when the computation is very, very large. So for many applications, really, we don't need this parallel thing. And so that's one thing that you can check if you have interest in those questions. The other one, if you really get into big data, so in that case the data sets are really like gigantic, so it's impossible to do things with just one machine, and you have to really have a network of machines to do things. And this was developed by Google years ago, and they have this technology that they call MapReduce. And this is some proprietary technology of Google, and MapReduce is a way to, when you have a very large data set and large computations to do, a way to break things in parts. This is the map part of the problem, how to divide things to give them to different machines, to the computations, and then how to put together the outcome of every machine. So this is the reduce part. So the map is breaking in parts your computation, and reduce is when you have the outputs of every part, how to put things together. This is the very general idea. Of course, you should look at least at the Wikipedia for those things to have a more detailed idea. And so this is the proprietary technology that you can use if you pay for those Google services, I imagine. And then there is a free alternative, an open source version, which is from Apache, the same from the servers, and it's called Hadoop. So Hadoop is a whole framework to do those big data computations. So in many books, when they explain things about big data, when it comes to the software, they say, okay, you have Hadoop and then you have R, like the two things that people is using for those. And so Hadoop is just another thing, and well, this is a whole wall here. So I'm just giving you the names, and if you don't know about this, you can check and look for more information. But this is free, and those the MapReduce thing, and is a thing that in big data is being used a lot. And then in R, what you have still is, if you use Hadoop, interfaces to Hadoop. And in some of the older books, this wasn't still very developed, and so I think that you should check from the present sources to find about what you have for this. So you have different packages that allow to communicate, let's say, R with Hadoop. So still, that means that you can use Hadoop, but also you can use R. So the thing with the efficiency is that R has this philosophy which is like the same that you have in general in Linux, which is the modular philosophy. So you don't have one thing that does every possible thing, but what you have is different small things that do one thing, and they do it well. And when you want to do complex operations, then you use the different modules or elements, and this is the philosophy. So in R, you many times end using other programs or other things to work, because they do it better, and R doesn't try to do all possible things well. So this is the path from R to really doing things with big data, which is using something like Hadoop. Beyond this, there are other services. I think that Amazon have, I didn't check recently, I don't know, but had this cloud machine learning service that was called Deep Lens and so on. Many of those things have this orientation to deep learning, to using those powerful neural networks, and many applications to things like face detection and things like this. So there are a lot of technologies here that people can use. Many are proprietary, like the Google services or the Amazon services and so on. But there are Hadoop or R, which are just free, open source, and anyone can use them. So this is a bit of perspective on parallel processing. So you might try some of those computations and see what happens with the different number of cores or on your different machine. Every processor, of course, will give different times. And also, I don't know if you're in Linux or in a Mac, what the differences could be. So if you can also try different machines, you could see what happens. And another thing is that some of those computations, like in welding models, have some random steps. So that means that if you do things again, the times may be very different. Because imagine that you set the coefficients for a neural network at random, and so it could happen that you get something closer to the optimal solution, and then the convergence is very fast, or it could happen that you have very bad numbers to start, and then it's very slow to get to to the optimal coefficients. So this is another factor that affects the time of computations. And those problems happened with all interpreted languages, so it's a bit of a paradox that the popular languages for doing things in machine learning are Python and R, and they are also the languages that are not the best for performance questions. But I think that it's better to have those languages with many development in terms of packages and which at the end are easy to use when you have the package done, than going to low-level programmation. I don't know really. In some cases, maybe you have to go the low-level programmation way, going to C or C++ or whatever. But, well, then maybe the problems could be other problems, I don't know. For basic computations, as you have seen in what we have done, the R goes really well, though we haven't done any computation that takes hours. And of course, if you get into neural networks, at some point you could have computations that take several days or things like this. But for the examples we have run that are meaningful because they come from real life, the performance was very good. So that's it for this video. And if I can do something with the GPU, maybe I could do another video explaining those things, but for this general view of the topic, I think that this is enough.